In the first course on statistics, we were introduced to the univariate normal distribution, among other distributions. Now that we're dealing with multivariate data, we will be utilizing the multivariate normal distribution. The multivariate normal distribution is similar in concept to the univariate, but works across multiple variables simultaneously, or what we will refer to as multiple dimensions. Right now, we'll focus on the visualization of the bivariate, which is 2 dimensions or 2 variables, and conceptualize the remaining dimensions. In general, we can have a single column or vector of data following a normal distribution. So consider class grades. Everyone focuses on what's the bell look like, what's the mean, what's the standard deviation. And this gives a student an idea of where they fall within the class. They're utilizing that concept of the bell curve or the normal distribution and the mean to relate to where they are. When multiple variables follow this type of distribution, that is, that it's multidimensional, it's called multivariate normal distribution. Now, similar to univariate techniques such as ANOVA and the t-test that require the data in the groups to be normally distributed, a number of techniques such as MANOVA and Hotelling's t-squared will require the data to be multivariate normal. It's difficult to find data that follow a true multivariate normal distribution, but just as the normal distribution makes it easier to visualize and work with the data, multivariate normal distribution provides a strong approximation of data. In addition, since according to the central limit theorem, larger samples will follow a normal distribution, the same premise is present for the multivariate normal distribution. Let's take a look at the univariate normal distribution. This is what the function is. 1 over the square root of 2 pi times the variance times e raised to the -1/2 x minus mu over the standard deviation and that quantity squared. From this, we know the mean, mu, and the variance, sigma squared, and the standard deviation. You may recall that the notation for the normal distribution is n, mu, and sigma. Now, the standard univariate normal distribution looks like this, n, 0, 1, where 0 is the mean, our standard deviation is 1, so therefore 68% of the data will fall between the -1 and 1. The normal distribution is the most commonly known distribution, but arguably the most important. It has the shape of the bell curve, and we know that 68% of the data points will fall within plus or minus 1 standard deviation of the mean. More importantly, as we'll see later, as you get more and more data, all distributions will tend to normal, according to the central limit theorem. So important concepts of the normal distribution are that it is bell-shaped, it is a continuous distribution, it has 2 parameters, mean and standard deviation. 68% of the data lies between plus or minus 1 standard deviation from the mean, 95% of the data lies plus or minus 2 standard deviations from the mean, and 99% of the data lies within 3 standard deviations of the mean. When referring to probability distributions, we want to carefully look at the curve and the area under the curve. Now, one might remember from calculus that a curve can be described as the area under the curve. For probability and statistics, this is an essential point. Consider the curve on the right, which is a normal distribution, with a mean of 0 and standard deviation of 1. The entire area under that green curve has a value of 1. And the mean line, which is dashed, splits the distribution into 2 parts. The left side is 50% of the curve, the right side is 50% of the curve. Again, recall that in a normal distribution, the mean and the median are theoretically the same, and this should be apparent from the graph on the right, because since 50% of the curve is to the right and left of the mean. This function provides this probability distribution of a continuous function and is called a density function. Now, the multivariate distribution is similar to the univariate, only in the multivariate analysis we're using matrices. This function is represented as such, where x represents a vector that is our test point, the mean vector is mu, and the covariance matrix is sigma. And the notation for multivariate normal is NP, which is normal distribution. The P stands for the number of dimensions, with a mean vector of mu and a covariance matrix of sigma. The bivariate distribution actually looks like the following. So consider the fact that in one direction we have one variable, and in another direction we have another variable. That's forming that box at the bottom. And each one is kind of going upward towards its mean and then falling back down away from its mean. When we put these two together, it kind of looks like a hill. So both variables have a mean of 0, and so our mean vector is 0, 0. Our covariance matrix is 1, 0, 0, 1. The way we interpret this is, remember that along the diagonals, it's representing the variance of each one of the variables, because it would be the covariance with itself. So the first column represents x1, the second column represents x2. Therefore, our rows represent x1 and x2 respectively as well. So the variance of each item is 1, and the covariance between x1 and x2 is 0, which means they're independent of each other. So these would be two variables that are normally distributed, each with its own mean of 1 and standard deviation of 0. If we were to look at it from above, we could create these contour lines where the top of the hill is that center circle, and then every circle after represents a certain amount of mass that is falling back towards the level ground. So this is what it might look like in a 2D plot from above. But what if we change something? Let's assume that we have a mean vector of 0, 0, and we've altered the covariance matrix so that there's a little covariance between the two variables. Now, from this graph, it's a little hard to see, but if we look at it from the top, we can see that there is a pull between the two variables. And if you recall that in the two-dimensional plot, if we were to do a scatter plot, we might see the points going from bottom left to top right, meaning that there is a correlation between the two variables. By creating these contour lines, if we were to look at it from the top, we would see these circles from in the very middle being the top of the hill between the two variables, and then it progressing outward and outward and outward. And this is what's going to give us a very richer look at data that is pulling together. The lines of the contour plots provide an area for equal probability of the multivariate normal distribution, in the same way that the standard deviations provide an equal area to the left and the right of the mean. As can be seen on the graph to the right, the contours are shaped in an elliptical pattern and are based on the covariance matrix. So to construct an ellipse, it consists of two parts. The direction of the ellipse axes are in the direction of the eigenvalues. The length of the ellipse axis is given by a constant computed as the Mahalanobis distance, which is referenced by this formula C, times the square root of the eigenvalue times the eigenvector. The distance constant C is analogous to a chi-squared distribution. So I've drawn the chi-squared distribution for you here with 2 degrees of freedom. We can compute the chi-squared using chi-squared P, which is the probability, in this case 0.95, with the degrees of freedom. So running this in R, we have the following. Q chi-squared 0.95, comma 2. Where does the 2 come from? There are 2 dimensions in our data set, so therefore we're going to be using 2. Therefore, 95% of the distribution is at 5.99, so our constant C is at 5.99. Assume that we have a bivariate normal distribution with a mu of 0, 0 and a sigma of 1, 0.5, 0.5, and 1. The covariance matrix has eigenvalues of 1.5 and 0.5, with the eigenvectors being 0.707, 0.707 in the first column, negative 0.707, and 0.707 in the second column. So we want to find a confidence contour where 95% of the probability will fall. And this will correspond to this chi-squared of 0.05, or what we did is 0.95, with 2 degrees of freedom. And that was our 5.99. In R, we have the code here for our matrix. We're representing S as the sample covariance matrix, the 1, 0.5, 0.5, and 1. We'll compute the eigenvalues of S, and we'll compute our C constant. 0.707, 0.7 times the eigenvector 0.707, 0.707. Axis 2 will be the same thing. Find a confidence contour where 95% of the probability will fall, and this will correspond to the chi-squared with 2 degrees of freedom at 0.05 level. So therefore, we end up with the items on the right, 2.12, 2.12, negative 2.12, negative 2.12. Here's what it looks like in the R code. Again, we've run the first 3 lines. We have our mu centered at 0, 0 as our vector. And we have our axis 1, mu plus the square root of 5.99 times 1.5, and mu minus square root of 5.99 times 1.5. Both are multiplied by the eigenvectors for column 1 and the eigenvectors for column 2. Now to draw our chart, we have a number of different pieces here. We're going to draw an ellipse, okay, using the ellipse package, with mu as our mean vector and sigma as our covariance matrix. Alpha is 0.05. We're going to do number of points is 100, so we need to provide some information. New plot is true, so we're creating a brand new plot. It's going to draw the actual line where we have a type of L, that's what gives it the line type, and we'll give it a title called MVN contour. Now what we'll do is we'll plug in some points. We're going to put in 0.00, so in other words, that's going to be at the dead center. It's respective to our center point or our mu point between both variables. We have x1, that's the square root of that chi-squared value times the eigenvalue, and then we take that value and multiply it by the first vector. And we do the same thing for y1, multiplying it by the second value of the first eigenvector. The opposite numbers, x2 and y2, will be the negation of those, minus x1 and minus y1. We'll do the same thing for x3 and y3, and x4 and y4. This will get us the 4 points that you see on the ellipse. From that, we will draw those points by using the points function in R, and it will give us our x1 and y1, our x2 and y2, our x3 and y3, and our x4 and y4. Then we will draw some line segments to connect the dots. We're going to connect x1, y1, and x2, y2. We're going to connect x3, y3, and x4, y4. So for any data set that follows a multivariate normal distribution, a few additional things are also true. Every linear combination of x is normally distributed. So theoretically, if we have multivariate normal distribution, any subset of x or any linear combination of x will be normally distributed. And that's important because it means that a few of the columns, if you have 6 columns that's MVN, you could take 3 and 3. Those should be multivariate normally distributed. In univariate analysis, a variable has a mean of x bar and a variance of s squared. In our multivariate analysis, a matrix sample x will have a mean vector of x bar. So this is our a vector of means. The multivariate central limit theorem states that if a set of n observations are multivariate normal, or another distribution, then the distribution of x would be normal will be multivariate normal with a mean equivalent to mu and a variance covariance matrix of sigma divided by the square root of n. In addition, this sample covariance matrix S, if we multiply it by n minus 1, will have a Y-sharp distribution known as W, with n minus 1 as the first parameter and covariance matrix as the second parameter, n minus 1 degrees of freedom. And this is related to the chi-square distribution. Therefore, given a set of independent observations from a population with mean of mu vector mu and covariance matrix sigma, we can identify the following 2 properties. The square root of n times x bar minus mu is approximately np 0 sigma, meaning that this value here, the square root of n times x bar minus mu, is approximately multivariate normal with 0 mean vector and a covariance matrix. Further, n times the mean vector of our sample, denoted by x, minus mu, our population vector, transpose, times our inverse covariance matrix, multiply that by our mean vector minus the mean population vector, is approximately chi-square distributed with p degrees of freedom. Thus, if the data have multivariate normal distribution, then all the previous properties will hold. We need to have a few tests, just as we do univariate tests, to assess normality. And we can do this using, again, the QQ plot, which compares the observations or their transformation to a known distribution, like normal, or computing a statistic and obtaining a p-value. Generally, assessing normality of multivariate data is more difficult and may not entirely be accurate due to the number of observations and p-dimensions, but not impossible. There are 4 statistical tests that provide information on multivariate normality. These tests include the Mardia test, which is based on the skewness and kurtosis, but recent research has shown that this test may not have significant power. Royston test, which is based on the Shapiro-Wilk test, and is very good with small samples, but cannot be used with greater than 5,000 observations. The Henze-Zerkler test, which is generally good with reasonable power, especially when the observations are above 75. And the Dornick-Hansen, which recent research has shown is reasonably good, but there's still some work that needs to be done with it. Farrell et al. In their 2007 paper recommend using multiple techniques as well as graphical analysis to ensure the multivariate normal properties of a data set. And this is one of the things that we've been saying for years in this class, is that you want to use multiple tests as long as the assumptions are valid to ensure multivariate normality. A dataset can be analyzed for multivariate normal distribution using the MVN package in R, so make sure that you have that downloaded. Each of the tests can be performed by passing the desired test into the MVN function. So here we have our example. We load our library, MVN, and we'll call the MVN function, notice it's in lowercase, against the iris dataset with the first 4 columns. We can't pass in the other column because it's categorical. We indicate the test that we want. So in the first example, we're passing the Mardia test. In the second case, we're passing Royston for the test. The next one, the Henze-Zerkler. And the fourth one, the Dornick-Hansen. So the test that's going to be performed is passed into the parameter called MVN test. Now, there are some additional parameters for plotting, such as univariate plot and multivariate plot, which will provide some of the associated plots. But for each of the tests, the hypotheses are the same. The null hypothesis is that the data is multivariate normal, and the alternative hypothesis is that the data is not multivariate normal. So what we're doing is we're looking for that p-value to be greater than 0.05 to give us an indication of whether or not the data is multivariate normal. When we run those lines of code on the previous slide, we'll get the following results. You'll see here, we've only displayed the multivariate normality. There are many different pieces that are displayed, like univariate normality for each of the observations and a few of the other metrics. But here we're just displaying the first object of each, which is the multivariate normality. In the Mardia test, you'll see that it gives us the skewness and the kurtosis. When we combine those two, both will have to be yes in order for the multivariate normal, indicated by the third line, to be yes. The Royston test to the right will provide us with a p-value, which in this case is less than 0.05, and therefore, again, we will reject the null hypothesis that the data is multivariate normal and state that we have evidence that the data is not multivariate normal. And the same holds true for the Henze-Zerkler and the Dornick-Hansen test. All 4 tests, therefore, provide evidence that the data is not multivariate normal. So a few key notes. Since all subsets of multivariate data should be MVN distribution, then we could look at bivariate sets of data. Thus, any relationship between variables should be linear and have a random pattern. A scatter plot could be very useful in assessing this. The scatter plot would be of 2 variables, or pairs of variables. Develop a QQ plot that's based on this Mahalanobis distance. We could use that to compute a QQ plot and use the chi-square distribution to get the values of Q. However, using a function of the Mahalanobis distance may be more appropriate. This Mahalanobis distance is an estimate of this thing called delta squared, which is a measure of the distance between point P and a distribution D. And it represents how many standard deviations away that point is from the mean of D in multiple dimensions. That's why, if you recall, we had the contours. The Mahalanobis distance is going to be measuring in multiple dimensions the point away from that central mean point of all the variables, or the 2 variables in the bivariate example. So if P is at the mean of D, the distance is 0. And this distance will increase as P moves away from the mean along each of the principal component axes, as they're called. It measures the number of standard deviations of P to the mean of D.